Hi class. So once again, let's think back to section 1B of chapter 5 where we were asking what determines air pressure. And so we had mentioned that the amount of pressure on a surface is determined by the pull of gravity. So we looked at, that's the first thing we looked at was the effect of gravity on air pressure. We also said that the kinetic activity of the molecules in a column of air will influence the air pressure, and so we looked at temperature in our previous video. And so now we're going to take a look at the effect of water vapor changes in a column of air or a volume of air, and explain the importance of those changes in water vapor on air pressure. Okay, so let's start off with a volume of air, and so what we're going to do, we're just going to draw a box. Okay, let's draw a box, and this box will will contain nothing but air. So if we remember what air is composed of, and we're talking about dry air here, we're going to start off with a dry atmosphere, no water vapor in it at all. That would be 78% nitrogen. And maybe make a little note to ourselves here. So dry air is 78% nitrogen, 21% oxygen, and 1% argon. We're not going to worry about that 1% argon for right now, okay? So we're only going to take into account nitrogen and oxygen. Okay, that should be O2. All right, so let's fill up our box, our volume, with nitrogen and oxygen. And if we were doing this correctly, and let's just randomly say, I guess not so randomly, what if we choose to say that this box contains 100 molecules, and so if it is a box of dry air, those 100 molecules would be, 78 of them would be nitrogen, 21 of them would be oxygen. Okay, so we're not going to be drawing in that many, but I just wanted to let you know that, the bulk of this box, 78% would be nitrogen, and we've got an oxygen in here every once in a while because oxygen is 21% of this box. So maybe an oxygen down here and put an oxygen here. Okay. Now, what we need to do to get our point home here about why air pressure changes across a horizontal distance, and the answer is because one of the reasons is water vapor changes, is we're going to have to now take a look at the atomic weight and molecular weight of molecules, atoms and molecules in our atmosphere. And so I know you all remember back to chemistry in high school and have got the periodic table of the elements memorized. Okay, what we're going to be doing is we're going to take a look at the atomic weight and the molecular weight of the various molecules that make up our box. Okay, so we've got nitrogen and oxygen in here, so if we're looking at nitrogen, okay, so an atom of nitrogen, but we've got here molecular nitrogen, so let's take a look at molecular nitrogen too. So the atomic weight of nitrogen is 14. Okay, but again, our nitrogen is molecular nitrogen, two nitrogen atoms stuck together, so the molecular weight of nitrogen is going to be 28. Okay, and then we've also got oxygen in here. So with oxygen, in its atomic form and its molecular form, in its atomic form, oxygen weighs 16. In its molecular form, two oxygen molecules stuck together, it's going to weigh 32. Okay? And so what we're going to do is we are going to introduce water vapor into our box, into our volume of air. Okay? So right now we've got a box of dry air. There's no water vapor in it, but we're going to introduce water vapor. So if we look at water vapor, okay, so oxygen has an atomic weight of 16. Hydrogen has an atomic weight of 1, but there's two of them. So there's 1 plus 1 is 2, plus 16, makes that 18, has a molecular weight of 18. Okay? And so there's a scientist from, back in 1700s, 1800s by the name of Avogadro. And basically his law is that when you have a volume of molecules, for every molecule that you introduce into this box, you have to remove a molecule in order to make room for it. Okay, that's Avogadro's law. And so if we're going to introduce water vapor into our volume, okay, let's go ahead and do that. And so let's put water vapor in here. All right, if we put water vapor in there, we've got to chuck out a molecule. So we introduce a water vapor molecule and we remove, in this case, a nitrogen molecule. Look what happens. We introduced water vapor, which has a molecular weight of 18. Okay, we had to remove nitrogen, which has a molecular weight of 28. Okay, and in doing so, we've reduced the mass of the air in this box. Okay, basically put the box on a water diet. Okay, if we introduced another water vapor molecule into our volume and we chucked out an oxygen molecule, so we introduced a molecule that has a molecular weight of 18, we chucked out a molecule that has a molecular weight of 32. So once again, we have reduced the mass of the molecules that are in our box. Okay, and so we've made our box lighter. Okay, and if we continue to do that, if it's a really humid day and we're adding a lot of water vapor to the air, it is replacing the oxygen and the nitrogen with water vapor molecules. Okay, and so the long and short of it is then that the result of adding water vapor to the air is that moist air is lighter and less dense than cold air. Than dry air, sorry. So moist air is lighter or less dense than dry air. Okay. And therefore, it exerts less pressure on that surface. Okay, so why does air pressure, one of the reasons that air pressure changes across a horizontal distance, it depends on the amount of water vapor in the air. The more water vapor in the air, the moister the air, the less dense the air is, the lighter that air is compared to dry air. And therefore, that moisture air is going to exert less pressure on the surface, okay? And so your atmospheric pressure is going to be less. Okay, so here's our third one. So again, the polar gravity, temperature will affect the average kinetic energy of the molecules, and then the mass of the molecules will also influence air pressure. So those are our three influences on atmospheric pressure.